Okay, let's start. We have our topic for this week is one particular topic on the inference in Markov random fields. Because Markov random, the Hammersley-Clifford theorem permits to use a so-called Gibbs random field for inference or as an equivalent representation for solving the task that one might want to solve with a Markov random field. But a Gibbs random field is a field of potentials. And when expressing these potentials as in a particular functional form, that is like e raised to the power of minus some function, then one can look at this function here as an energy term. Energy term in the sense that it is a function that achieves the desired solution when it reaches a minimum. So it's like a performance assessment function where the best desired result is a minimum of the function. Okay. And then one has in principle access to all the tools that are available for solving energy minimization problems, which is actually plenty. And one tool in particular that we're looking at here is the so-called graph cut-based solution. So this is the topic for today. As usual, I prepared a couple of questions that essentially follow up on the topic. But before we go into this, I would also be happy to address anything else about like the material or so. If you want me to emphasize something or to clarify something, we can start with this. Yes, please. Mm-hmm. Which slide, sorry?
Part 26, slide 1.
Yes.
There probably something very simple, but I have struggled to understand what happened to the partition function category and
Yeah, it vanished. This is actually true. I mean, I might have written it there, but so we could have written 1 divided by capital Z times all of this stuff or so. But in fact, when it comes to the choice of labels, the partition function is a constant because I think it's important. Okay, so we have this expression here. So the line above, yeah, we have something like the sum of all these energy terms e raised to the power of minus all these energy terms times 1 divided by the partition function. So these energy terms are evaluated for one particular assignment of labels to the hidden variables. So if we say, for example, we want to denoise an image, so let's make a very simple image. So just a circle with a uniform background. if the input is something noisy, and we want to get to the denoised image, then every pixel would be a hidden variable. And of course, we hope that whatever we do here, it's a formulation that helps us to get rid of these little noisy pixels. Yeah? Okay. So what we are assessing here is the quality of one particular choice of binary labels. Like this would be the ideal solution. I mean, sort of obviously, no? But an alternative could be a solution that looks like this, or an alternative could be a solution that looks like that. So what we are assessing here is one particular input of these. We say, okay, like we're interested in that single input that argmaxes this expression. So we're looking for that labeling out of all these choices that maximizes the whole thing, so it minimizes the energy term. And the role of the set here is to divide by an appropriate value such that this is a proper like probability distribution, you could say, that it's like normalized such that it integrates to 1. So the set is the sum over all labelings of all these distributions. So it's the sum over the e to the minus of this image, e to the minus of the other image, and so on. So since it integrates over all possible, or it sums over all possible like inputs, it doesn't change with one particular choice of the input. So in that sense, also the maximum, or then if we only look at the energy terms, the minimum associated with this is independent of the partition function. Or if you look at it from the perspective of a probability distribution, if this is the space of all possible labelings, then what we are looking for is the maximum likelihood solution, you could say, like the most likely solution. But what the Z does, the Z scales this distribution, but it doesn't change the location of the maximum. So, and then it's true that it just vanishes, it seems to just vanish. But if we write it without the set, then actually the similarity to other energy minimization problems is a bit more apparent, maybe. Yeah, so that was, yeah, but yeah, good thinking. Okay, anything else? Shall we, yeah? Oh, physical 17, like this. Why, can you say this again? Still not sure whether I properly heard it. So let me try to respond, and if it's not fine, then you can follow up. Yeah? Okay. So So the S is identified with the label 0. The T is identified with the label 1. So that means if these two edges are cut, then both variables, the Zi and the Zj, are on the side of the label 1, so they get the label 1. So the cost for cutting these two edges should be the cost for assigning the value 1 to both labels. Now, it was my understanding you were interested in these crosscuts, is that right? Ah, yeah, this graph has 5 edges. Ah, yeah, right. So I think, okay, so if the idea of the cuts is fine, no? So if you say, okay, I cut here, I have this label assignment, I cut there, I have that label assignment, then I still have to answer the question, okay, like what specific weights should I assign to each individual edge in this graph? And then it turns out if I count the edges, I have 5 edges, but I have only 4 numeric values that I could possibly assign, like these 4 energy terms. So it's underdetermined. So if I try to come up with a linear system of equations or something to solve this, then I'm missing one value. So it doesn't work. But then it turns out that it doesn't need to work because so the paper is a bit obscure at this part, but let me try to skip the details and just say, like, for any energy term that satisfies the submodularity condition, yeah, you have a certain relationship. And actually in all our problems we do have, like all problems that I'm aware of, we have in particular the relationship that a 0-0 labeling creates lower cost than a 1-0 labeling, and I think a 1-1 labeling creates lower cost than a 0-1 labeling or something like this. Yeah. Okay. Like whenever that holds, and then you can use a simplified replacement graph that only has 3 edges, and then suddenly, okay, you can say, okay, not a problem. I have 4 values. I have just 3 edges, so I can calculate. These the specific weights for these 3 edges, and it's solvable. Yeah. Okay. I didn't check too thoroughly the rear part of this. So if we look at the paper is fairly long. It's like 13 pages. It starts with the case that is relevant for us. So energy functions that consist of a unary term and a pairwise term. They then extend it to energy functions that also have 3 hidden variables involved. And then they go on and prove stuff and so on. I didn't go through the rear part of the paper because I had the feeling that, well, I'm not really aware of applications that make use of these like 3 variables or so. So I thought it's okay, we can skip it. No? But it could be the case that there are further details added later that I didn't check. No? Okay. But for all purposes, like we will always have functions of this form, so we can always use a replacement graph of this form. Okay. Okay. Shall we continue? Yeah, so I prepared a couple of questions. Some are very literal, just repetitions of stuff, just to make sure that we have them. What I think can be quite useful is if we repeat, like, and just try to sketch what such a cut looks like. But it doesn't need to be the first task necessarily. So we can also first talk about the constraints, or like what was this homomorphism. This is more or less like just a restatement of the slides. This can be a useful exercise, that we construct a unary potential, and then okay, so here's also a potential function, just for the sake of discussion, that we can use. Okay, so maybe to go quickly, maybe to start with task 2 and 3 or so, to have the facts checked. Yeah. So this graph cut transformation, it works for a very broad range of energy functions, but these energy functions must have a special form. Yeah, this was what we saw in the paper. Here's a summary of our results, equation number 1. So they must constitute a sum of unary potentials, or unary energy terms, sorry, and a sum of pairwise energy terms. So starting from there, so if it's something like this, over all Z, so if we say this graph cut solver can always be applied if there's a function of this form, then we can go backwards, say, okay, if we can only use an energy function of this form, we can go backwards to the Gibbs random field, and essentially backwards to our Markov random field, and can say, okay, no? So so we can have at most 2 hidden variables per term. Yeah. Then something that that is not really visible from this equation, but it's written somewhere else, that it's only globally optimal if these are binary variables. And then the third thing is, in the paper, it's called the regularity or graph representability condition or so. It's the submodularity condition. So it goes by different names in the community, but yeah, a function E of n binary variables. No, sorry. Where is it? Here. Graph representable. Okay. E is graph representable if and only if each pairwise energy term satisfies the inequality that the cost for identical labels is lower than the sum of costs. Sum of costs of identical labels is lower than sum of costs of different labels. Yeah. So this is the third condition which in other parts of the literature is called submodularity condition. So this is equation 7 in the paper. Okay. I don't know, what do you think? I always have the feeling the submodularity condition is not a very surprising request in a way, in the sense that it kind of implies if you don't have a reason to change the label, then you shouldn't change the label. No? So it's like it's cheaper to keep the label, no? But of course there can be circumstances where you just have to change, no? And in that case, of course, you should, no? But the relationship between two hidden variables should be, well, I'm encouraging that neighboring labels are the same, yeah? Because this is the role of the hidden variables. And the role of the unary terms is to say, okay, but my observations kind of force me now to change the label. So, okay, so I change it, no? If there are too many differing observations, no? But for the pairwise terms, they should always be in favor of sticking to the same label. So to have lower energy for two identical neighboring labels. So that's the whole point of this equation. Yeah? Yeah. Okay. So these are the three constraints, and I think they are kind of important, but in practice, of course, people already craft their problem description in such a way that they are implicitly satisfied. No? So it's not something that one has to check necessarily. There was this mentioning of a homomorphism, no? And this is, I think, this is one of the really strong tools that this GraphCut paper here brings forward. Where is it? I have to search for it. Let me show it to you in the slides. Here it is, sorry. So I think this is really a powerful concept. And I think in like the basic math classes or so, it's never really clear like why learn about stuff like homomorphisms or so, because the applications are missing. No? So here's a specific application. No? So this construction idea that the solution of the whole graph can be found by thinking about solutions for every single of these terms and then just adding them together, this is really what makes it possible to craft this graph cut solution. No? Okay. So yeah, so if graph 1 encodes the minimum of an energy function 1 and graph G2 encodes a minimum of an energy function E2, then the union of these graphs encodes the minimum of the energy function 1 plus the energy function 2. No? And this is exactly the point here, that we are adding, like our objective function is just the sum of all these energy functions. Let's sketch a graph, or two actually, a unary potential and a full graph. So let's say we have binary labels 0 and 1. Draw a minimal graph for a unary potential with potential function Ez equals 4 times x minus z plus 1, and provide the numerical edge weights for x equals 0. Okay. Okay, so we have a function exz four times x minus z plus 1. And the observation for this hidden variable is 0. And we have binary labels. So we seek this little graph snippet for a unary potential that encodes this cost function. What does it look like? Yeah. A source and a sink, and in between what? The hidden variable. Yep. Okay, and now? Then we need the weights, yeah. So what weights can be assigned to each edge? Yeah. Mm-hmm. So if we cut here, so the source corresponds to 0, the sink corresponds to 1. No? So if we cut here, this would correspond to assigning a 1 to the z, because then it's on the side of the t. So the cost associated with this cut, x is 0, would be to have a 0 and a 1 here. And the cost associated with a cut here would be the cost for having a 0 here and associated, and having a 0 assigned to z. So E00. We can evaluate the function. It's 5 and 1. And then, strictly speaking, it says like a minimal, does it say? I think it says something, a minimal graph, yeah, for a unary potential. So we can say, okay, we can also save one edge here, yeah, and replace it by a simpler graph that only has an edge weight of 4 here, so 5 minus 1. So only the difference in cost between the left edge, which costs 5, and the right edge, which costs 1. So to say, okay, for the purpose of the optimization, we have to make a choice between cutting here or cutting there. So it's fine, we only need to write down the difference. Yeah? And this will be embedded in a bigger graph, which we can think about now. So let's draw a bit of a bigger graph. So we can simplify this a little bit. No? So we can say, okay, like, what if we have, again, like a simple image, no? With something black in the middle, no? White in the background, a bit of noise here and there. And the task is to denoise this. What would the graph look like for the whole thing? No? Yeah, we can start to lay out the image a little bit. So let's say this is the image, yeah, and there are a number of these hidden variables that constitute the pixels of the image, yeah. So these are supposedly black. Well, so this is the eye here, and this is the background. So if this is our source, and this is the sink. Let's distribute the unary potentials first. Yeah? So the unary potentials, they only introduce an edge where, like, for the wrong connection. No? So if we would cut here, we would assign black to this node, even though the observation, or if 0 is black, let's make 1 black, it makes more sense. Okay, so 0 is white. If we cut here, let's make this white and this black, yeah? If we have a white pixel here, then it would be cheaper to cut down here because it's white. No? So for a unary potential, we would only include an edge from the source to this white pixel. For example, if this would be the cost function, no? It would be with a cost of 4 or so. No? To say, okay, if there might be reasons to cut here, but if you do so, it costs 4. Yeah? And all white pixels would get a link here with cost 4 for the unary potentials. No? For all black pixels, the reverse argument holds. So a black pixel, if we think about the associated unary potential, okay, S is white. We have a hidden variable, we have T equals black. So for a black pixel, it would be more natural to assign it to black. So it should only cost something if we make a decision to break this assignment to black. So black pixels get an edge here with, I don't know, if we have the same cost function, it would also cost 4 to assign, to break this assignment of the black pixel to the node. Yeah? Okay. And this, like for all the black pixels, we would have little edges going down here. And for example, if we have a little noise pixel here that looks black, no, then it would also be connected down here, even though its neighbors are maybe all white, because this is actually background, yeah, and are hence connected with the white, with the source node. Yeah? This is the situation for the unary potentials. But before we go to the pairwise potentials, I just want to make sure, are we okay? Is it okay? Yeah? Okay. Then let's go to the pairwise. The pairwise potentials, okay, solving these equations is a bit more complicated. Let's not do this. But what do these links look like that we are introducing for the pairwise potentials? So for energy terms, for the pairwise energy terms. So, for example, if this is zi, yeah, and this is zj, just for the sake of example, we would add a little bit of weight down here. Then we would add a little bit of weight, like whatever it is over there. And then from here, we would add a bit of weight down here to the t. Yeah? And this actually would happen for all neighbors to this node zi, no? Because this node has not just this neighbor, but it also has this neighbor down here. So we would also add a connection to this neighbor going down. And it also has this black pixel here as a neighbor. No? So it also goes over there and from here downwards. Okay, so this node here has these 3 neighbors connected with these pairwise terms. You know? And now, if we look, so the optimization problem, or the cut, makes a globally optimal decision. So it will find an assignment here that makes the cost minimal for all these edges. I mean, would be too many edges here to draw them, no? But for all edges simultaneously. This means that, for example, I mean, ideally, the assignment here of this black pixel with the unary potential to the sink would be overridden by the pairwise terms that this node would have in relation to its neighbors. No? And the outcome would be that it's cheaper to cut down here and to preserve these 3 neighbors and to make this pixel white instead of sticking to the unary assessment, oh, it's a black pixel, we should keep it black. No? Okay. So if we're trying to draw this like cut, the ideal, the envisioned cut, no, would be something like that all these pixels here on the right of the eye, they should be cut down here, no? And then we would like the cut, so this everything down here would be cut, and then it would say, okay, now the letter I, this is a black letter, so the cut has to go on top and sever all these links to the source here for the letter I. And then again dive under these hidden variables to cut them again, because they should be white again. So they have to be cut from the sink. No? Does that make sense? And the cut, I mean, it can go up, down. It can change the side all the time. No? In principle. Okay, just wanted to visualize this somehow. I mean, the optimization itself is fully automated. No? It's just this like graph algorithm that runs through. And of course, the graph itself, for a realistically sized problem, it's much too large to be visualized. But still, it's a fairly effective method. If we recall from from last week, the slides. In the book by Bishop, there was a little example output here. So this is an example output for the graph cut algorithm. And okay, it left some noise pixels there if they happened to lump together. So if there were multiple noise pixels ending up at the same spot, the algorithm, the way how the weights were chosen and so on, decided to not smooth over them. Yeah? But all isolated, if we compare it with the original input, no? Like whenever there was an isolated variable or so, it just got removed by the algorithm. No? So in that sense, and I think these spots that are left over with multiple black spots in place, they are kind of testament that yep, you could anytime you could say, okay, I'm going over this and I preserve this structure. It looks like a structure, I preserve it. And then it's not deleted. Yeah. Maybe just a quick check. I mean, these potentials they could also have some weird functional form. No? So don't be. I'm not sure how practically relevant this is, but just don't be fooled by it. No? So as long as as long as the energy function has a recognizable minimum at the like desired spot, like for a pairwise potential or pairwise energy term, if for identical labels there's a minimum, no? Or for unary potentials or the enclosed energy term, if for an agreement between the input and the hidden label, there's a minimum, that's all fine, no? It's all fair game. How much sense it makes to play with these energy functions is a different question, but from a mathematical point of view, it works. Yeah? And the only thing that one has to keep in mind, if you have more than two labels, then you have to do something approximate, like this alpha expansion algorithm that at one time fixes one gray value, checks can I put more pixels to this gray value. If it gives a lower energy, I keep it, and I pick another gray value and I iterate over this. That's all. No? Okay. And it's not globally optimal anymore, but it's still good in terms of that it's just by a multiplicative factor away from the globally optimal solution. Multiplicative, if you consider the residual energy as a loss function, then you're only a multiple away from the minimal loss. But this provably. Okay. Yeah, I think that was all that I had for today. Are there other things that you want to discuss? Yeah. Sorry. Yeah. Oh, this is actually the margin, like it's only a margin away from the theoretical optimum. This is a mathematical proof, actually. It's in the, I think it's in the appendix of the paper, but I haven't prepared it, to be honest. Yeah, it's, but I think they also only copied it from previous work, but I'm not 100% sure. But in fact, in the years immediately before these like very deep neural networks came up, the alpha expansion algorithm was massively used, like for any segmentation task or so. It was literally the best tool out there, and it's still. I mean, if you fairly compare compute, no? Then it's massively cheaper than using a neural network, no? And like given that, so it's a good trade-off if you don't need if you need something below a network, no? Then it's a good method. Despite the fact that it only finds a local optimum. Yeah. Okay. So we don't have a lot of things left on our agenda. I have this intention to look with you at variational autoencoders, which is a particular construction, let's say, of a neural network. But in the justification of the method, what we will see is a lot of like pattern analysis methods. So I thought it's a nice bracket to kind of close this semester. This is the goal for next week. We will meet again on Thursday. This Thursday we will still have a meeting, but then the week thereafter, there will be no Thursday class. And we, in 2 weeks from now, we can, or you can prepare already if you want, that we do, like we talk about anything that you want to follow up in view of the upcoming exam, because the week thereafter, then there will be the written exam. Yeah, so it might make sense if you already organize the material a little bit, such that we can get some benefit out of this Q&A meeting. I'm not going to prepare something for myself. I mean, but you can bring like anything to the table that you might find relevant or so to iterate on. Okay. Okay, but this is in 2 weeks. So next week we have the variation autoencoders first. Then with that, thank you and see you then.